You remember what we studied in the last lecture?
The
So
CMOS
you
inverter.
discussing the quiz question as well today.
Why is it not clear? Okay. So let us discuss. So in the last lecture, first of all, we were discussing about the static characteristics of CMOS inverter, right? So we have discussed the basic idea of CMOS inverter, and also we have discussed the switch model of the inverter. So in this lecture, we will study about the static behavior and voltage transfer characteristics. So let us discuss. So what is the lecture number today? It is,
Sir, I think it's 11.
you think it is 11, okay. So what is the date? Date is 16 to 2022. Okay. So let us start with the static behavior of static behavior of CMOS inverter. So let us discuss a few points related to CMOS behavior, static behavior. So first of all, I would like to say that is it has high noise margin, high noise margin, ideally equal to supply voltage. So what is the supply voltage? Here. And second is ratio less logic level. Ratio less, one by one we will discuss logic level. Then third point is low output impedance. Low output impedance. So this is the characteristics of static behavior of CMOS inverter, low output impedance. So as a result, what will happen? Less prone to noise. Less prone to noise. After that, high input impedance. High input impedance. So which means that it improves the fan out. Improved the fan out. Last characteristics of static behavior is no static power consumption. No static power consumption. So one by one we will discuss. First of all, we will discuss about the we will start from the last point, that is static power consumptions. First we will discuss. So what do you mean by the static power consumptions? So first let us discuss here static power. So first we need to understand what is static power. So the static power basically means that when the device is not operating, not operating means that CMOS inverter is not switching, right? Between 0 and 1 or 1 to 0. Then in that case, we can define that the device is in static operation. Okay. So what does it mean? The static power. The static power means the device. So static power basically means that the when the device is not switching, or not switching means not operating between 0 to 1 or 1 to 0. When the device is not operating, right, or switching, between 0 to 1, between 0 to 1, or you can say 1 to 0, right? So we define that to be in a static operation. So we define that to be in a static operation. Okay. So which means that when you give, let us say, logic 1 to get, so whenever you will apply the logic 1 in the input signal, then what you will get? You will get logic 0 output, right? Or you can say if you supply the 0 input, then you will get output 1. So you are staying there for infinitely long duration of time, then we define that to be a static condition, right? So we are not giving the signal in the pulse form, right? So we can say that the device will stay there for an infinitely long duration. That means that we are operating the device in static mode. Okay. So what is dynamic mode? Let us say what is dynamic mode, right? So what do you understand by the dynamic mode? So dynamic condition is when you have a repeated switchings available to you, right? So repeated switching means whenever you give the input signal in the pulse form, then in that case you will have a continuous switching of the device. So that condition is known as the dynamic condition. So what then is in static power, since there is no switching, switching is not occurring in case of static condition, then you can say that, therefore we can say that static condition, we can say that there is no power consumption. There is no power consumption, but this is ideal case, right? There is no power consumption, right? So this is ideal case. Always remember, this is ideal case. So there will be no power consumption, means zero power consumptions. But why? What is the reason behind it? What is the reason behind it? Why the power consumption will be zero? Right? So in a static case, what happens? In a static case, that so in a static case, when let us say you are applying the, let us go to the circuit diagram, then you can understand here. So let us say this device. Let us say you have supplied the 0. Okay. So if the input signal is 0, then you will get output. But what will happen to the M1 and M2 transistor? M2 will be for 0 input, M2 will be on and M1 will be turned off. So there is no direct path from VDD to the ground, right? So the circuit is not in closed path. So what does it mean? If the circuit is open, that is M1 is open, it means that there will be no direct flow of current from VDD to the supply, VDD to the ground signal. This is known as G and D. G in D, right? V ground. So in that case, the circuit is not completing. As a result, what will be the current? If you see the circuit model, switch model, see here, what is happening in this model? Let us say this is the switch model, right? So what will be the overall current in this case? Yes. So there will be no direct path available. Okay. So what happens in a static case that do not have any direct path? As a result, direct path between VDD and ground. and ground. So you can say V, G and D here. Ground. Whenever you give, let us say, logic 1 or 0, you can say, there is no direct path between VDD and ground, right? So you will never have a short circuit. You will never have a short circuit in this case, right? So short circuit current available. Between VDD and ground. If load is not connected, always remember, if load is not connected, and ground. Okay, so that means that the static power dissipation level, the static power dissipation levels are very less, or typically less, or typically very small, right? Now let us talk about the second characteristics of static behavior, that is high impedance. So let us talk about the high impedance, high input impedance. Okay, so high input impedance, input. So if you remember the device structure of MOSFET, then you can correlate the input impedance. So let us say this is N plus, this is, let us say this is source and this is drain, and here this material is the silicon dioxide, that is, and here is a metallization, that is gate, right? So this material is known as SiO2, that is insulator, right? So this is P-type substrate bulk material. So what is the gate current for this? What is the gate current? If you remember, if you recall, so what is the gate current for this device? What is the value?
Sir, ideally it should be 0.
It should be 0, right? Good. 0 ampere. Why it is 0 ampere? Because of this insulator, right? So what is the definition of impedance? How can you calculate the definition, calculate the impedance? So let us input impedance, that is, impedance means here we are talking about the resistance. So the impedance is equal to change in voltage by change in gate current here, let us say. So we know very well the gate current for this device is 0, right? Because this is the input terminal, right? Gate terminal is our input terminal. So there will be an input resistance here. So since the gate current is 0, so what will be the ideal value of impedance, input impedance? Yes? Therefore, ideally, the input impedance will be infinite. Very good. Impedance is equal to infinite, and practically it will be very high. Practically, if we talk about, then it will be very, very high. Okay, because high, why it will be very, very high? Because there will be some leakage current there. So because of that leakage current, so we cannot say the input impedance will be infinite. But yeah, definitely it will be practically high. Now, so what will happen? So because of this high input impedance, so this high input impedance will help you to improve a fan out, will help you to get or to improve a fan out. So what do you understand by the term fan out? You have studied the fan out in basic electronics in digital electronics unit, that is unit 4 and 5. So what do you mean by the fan out? So fan out, if you talk about the fan out, so let us discuss about the term that is fan out. So fan out is defined as the capability of a single device deriving a number of such devices, right? So fan out is defined as the capability of a single device deriving a number of devices, a number of such devices. So let us say such. So for example, let us say this is a NOT gate, right? This is an inverter. So let us say we are connecting a number of devices at the output of the first inverter. So, okay. So here, this is the first device. So if I ask you to find out the fan out by observing this circuit diagram, so what will be the fan out here? So just you have to observe according to the definition how many devices are connected in the output of the first device. So how many devices are connected here? Yes. So what will be the fan out for this configuration?
4.
It will be 4. Very good. So the fan out for the above circuit is it will be 4. So therefore, let us say since the input impedance of the ideal case is infinite, so what will be the ideal number of fan out for an ideal device in a static mode? This is a very important point you have to remember. Therefore, in a static mode, since the input impedance is infinite and fan out, the capability of deriving the n number of devices, such devices will depends on the input impedance. It is directly, you can say directly related, directly proportional. So since the input impedance of in a static mode is infinite, so what will be the number of fan out in a static mode ideally? Yes. So fan out will be ideal. I will be infinite, but this is ideal. Okay. Now, so this is okay. So this static mode of operation is also known as steady state mode. Steady state mode. Now, what happens in case of transient response? So in case of transient response, it is degraded. Means the transient means that giving a rising or falling pulse, which means that at any point of the time, you are charging or discharging the capacitor. So when you will get the logic 1 in the output, if you see the switch model of the MOS transistors, then you can realize that while charging of the capacitor, you get the logic 1 in the output. While discharging of the capacitor, you get the logic 0 in the output. Right? So it means that at any point of time, charge or discharge a capacitor, right? So transient means, transient means giving a rising or falling pulse, which means that at any point of the time, charge or discharge a capacitor. So let us say if your fan out is high, so at this node, you have actually see a large number of capacitor. Let us say fan out is high, right? So here for each device there will be a capacitor, right? So at this node, you will observe that there will be a large number of capacitors. So there will be a large number of capacitors. So therefore, to charge or discharge a larger capacitor, you require a large amount of time, right? So as a result, what will happen? The speed of the system, speed of the CMOS transistor will slows down, and what will happen? It will degrade the frequency performance of the device. So in transient response, what happens exactly? The speed of the device slows down, and also the frequency performance of the device degrades. But what is the reason behind it? So because of the high fan out, there will be a large number of capacitors. So to charge and discharge the larger capacitors, we require a larger time, right? So because of that, the frequency performance and the speed of the device degrades. Okay, now we will discuss about the third point, that is output impedance. Output impedance. Okay, so see here the output impedance. So output impedance, it is usually very low, very low. Right. Now, so it is very less. Since the output impedance is very low, this is the characteristics of a CMOS device. Since the output characteristics is very low, so it is very less prone to noise. So since the output impedance is very low, so because of that, it is very less prone to noise. So which means that there are many noise sources inserted at the output of the NMOS. So it could easily reject it. And have a noise-free environment, and therefore signal to noise ratio at the output are typically high. Right. So what will happen because of the low output impedance? Let us say you are inserting. There are any noise sources inserted at the output of NMOS, so it could easily reject it. It could be easily rejected. So and have a noise-free environment. And therefore, if noise will be less there, then what will happen? So therefore, signal to noise ratio. So we know very well the definition of signal to noise ratio. SNR at the output are very are very high. So we know very well SNR, which is equal to output signal power. It is defined as the ratio of output signal power to the noise power. Since the noise is very low in case of CMOS inverter, therefore the signal to noise ratio will be very high. Noise power. Okay. Now, so what will happen in that case? So now we will talk about the another parameter, another characteristic, that is ratio
Sir,
less. Yes.
sir, how would low output impedance means that the device is less susceptible to noise?
Yeah. Because when the low impedance, when the output impedance will be low, right? So output impedance will be low. It means that you will get the high logic at the output, right? So you will either get what are the output signal for the CMOS inverter? Either 0 or 1. So as I told you, the logic 1 means that it has the signal will be VDD, right? And the logic 0 means that the signal is 0. So what will happen in that case? Whenever the output impedance will be low, it means that it will have the high driving capacity also. So the output impedance is low. It means that the frequency performance, let us say if you talk about the gain, that is gain is equal to V out by V in, right? So because of the high input signal, right, the gain will be high for the MOS transistor. So it will result in high gain, right? So it has we designed the CMOS converter, CMOS transistor in such a way that it has the capability internally to reject the noise, right? And we also know that CMOS inverter is a unipolar device. CMOS inverter is a unipolar device. It means that there will be a current will be only due to the majority charge carriers. So there will, because of the absence of the minority charge carriers, there will be no noise, due to minority. Because if you see the semiconductor device, in most of the semiconductor device, the noise arises due to the minority charge carriers. Since minority charge carriers are absent in CMOS devices, therefore the noise is very, very less. Minority charge in the case of CMOS device. Okay. Now, another term, that is ratio less logic level. So this parameter, first of all, we need to understand what is ratio less logic level. So it tells that irrespective of the aspect ratio. So first of all, we need to understand what is aspect ratio. Then we will talk. Aspect ratio. Aspect ratio is the ratio of width of the device to the length of the channel. Width of the device by length of the channel. Length of the channel, right? So it tells that is ratio logic level tells that irrespective of the aspect ratio of PMOS or NMOS, the static behavior is independent of that ratio, right? Let us say, so it indicates that irrespective of the aspect ratio of aspect ratio of PMOS, or you can say NMOS, because in CMOS inverter we connect both, that is PMOS and NMOS, that is W by L. The static behavior is independent of that W by L ratio. So what does it mean? It means that if you see the circuit diagram or device structure here, let us see here, this one. This one. Let us see if the device is operating in static operation, static mode, and if you changed the aspect ratio of PMOS, then still in that case you will get the same logic in the output. Or let us say if you are changing the aspect ratio of NMOS, in that case also you will get the same logic in the output. So the change in aspect ratio is not going to change your output signal. So this is the meaning of ratio-less logic level in static mode operation, right? Because for any device, since if we design the symmetrical, if we design the CMOS inverter using the symmetrical PMOS and NMOS, and due to some reason, if you are changing the aspect ratio of NMOS and PMOS, then it is not going to affect your result. You will get the same logic at the output. So this is the meaning of ratio-less logic level, right? Now, the second point, so which means that, let us say you are going to change any W by L ratio, you will still get the same logic, that is 0 and 1 and 1 to 0 transition. So which means that for any value of W by L aspect ratio of NMOS and PMOS, I get the logic levels available up to the till VDD. Okay. Now let us discuss this, the another point, that is high noise margin and ideal equal to supply voltage. So let us draw the circuit diagram here, then we will try to understand the characteristics of, okay, see here, one more important point. Okay, so let us draw first. Okay, this is okay, so this one. So where is the output? Output will be here, that is V out, and we are going to connect the capacitive load here. So we very well know that why we are connecting this capacitive load. So what is the reason behind it? Anyone can explain? What is the reason behind it? We are connecting the capacitive load instead of resistive load. Yes, we have already explained in the last lecture. Okay, so let us say here you are connecting VDD. This is, if you remember, this is source, this is drain, and this is source. So let us say this is M1, this is M2. So M1 is equal to PMOS and M2 is equal to NMOS. Okay. So now we will see the responsibility of each transistor here. So what is the responsibility of M1 and M2? So if you see the M2, that is NMOS, oh, wait, NMOS is responsible for the transition, that is 1 to 0, right? So if 1 to 0, so this means that it will act as a pull down device. Pull down device. So you can also say that PDD. Okay, now if you talk about the PMOS, so it is responsible for 0 to 1. 0 to 1 transition. So it means that it is acting as a pull up device, right? So we can call it as a PUD. So if you see the circuit that is above the output voltage, output signal, output terminal, you can say this is pull up device and this one is pull down device. Okay, now if you see the switch model, let us talk about the switch model. So case first here, that is when V in is equal to, let us say, VDD. So what will happen in that case when the input voltage is equal to VDD? So what will happen to the NMOS and PMOS? First let us discuss about the NMOS. What will happen to NMOS? Yes, NMOS will be open or short circuit? I mean on, turn on. Turn on, right? It will be on. Now let us discuss about the PMOS. So if that NMOS is on, it means that it is off. So if you draw the switch model, so see here, we are not going to consider here the capacitive load. Just let us say this is load free. So here, V out. Now we have to check which path the output will follow. It will go upward or downward. Or let us say, no problem, capacitive load. Then you can understand. So which path now it will follow? Or you can say that the capacitor will discharge or charge. In this case, let us say this is R1, Rn. Okay. So what will happen in this case? Yes?
Discharge.
Discharge, very good. So in this case, the accumulated charge across the capacitor will discharge. So in this case, we can say that the output signal is output terminal or output node is connected to the ground. Correct? So this is connected to the ground. So now, second case we will discuss here. Then we will write a point about it. So why it is connected to the output? Okay, we will discuss why the output node is connected to the impedance. Sorry, ground node. Because at the ground node, the impedance is low, and we also know very well the output impedance of CMOS is also low. So okay, now we will discuss. Second case we just discuss here. Let us say when V in is equal to 0, right? So what will happen in this case? NMOS will be off and PMOS is on. Okay, so now what will happen in this case? Let us, this is VDD, here also VDD. So this will be replaced by a resistor, that is, let us say this is RP, and here there will be a switch. Okay, so the output is here. Let us say this is capacitor. So now which path it will follow? That is this way, right? So now what is happening here? The capacitor is charging. Okay. So in this case, what we can observe that output node is connected to VDD. So for any voltage source, now I would like to ask here from the basic electronic course, let us say this is voltage source, that is Vs. And if I ask you the impedance of this voltage source, so what will be the voltage source? What will be the impedance for this voltage source?
So
Right?
infinite.
Not infinite exactly. For any voltage source, ideally the impedance is 0. Or practically, you can say, practically it is very low. This is all about the voltage source. However, your answer is correct, but for the current source. So let us say talk about the current source. Ideal current source. So here, let us say this is the terminal. So we always connect the high input impedance across the current source. So if you see here, you have to remember, if I say the impedance for the current source is infinite for ideal source, However, practically it is very high. So your answer is also correct, but only for the current source. It is very high. Okay. Now, here, if we see the supply voltage, that is VDD, so this is voltage source, right? So ideally, for the voltage source, or practically you can say, what will be the impedance for this? It will be very low, or you can say 0, right? So that's why output node is, in this case, is connected to the VDD, right? So what we can observe that here the switching is occurring between the ground and VDD. That's why you are getting the output signal either logic 0 or logic 1. Whenever the output node is connected to the ground signal, then in that case you will get logic 0 output. And whenever the output node is connected to the VDD, then in that case you will get the output logic 1. So the output node is either connected to a ground. And why it is connected to ground? Because we know very well the impedance of ground is low, and the output impedance of CMOS is also low. So that's why always it follows the low impedance path. So it is output node is either connected to ground or to VDD. So it is never floating. Always remember, output signal is never floating. So it is never floating. Oh, sorry. It is never floating. Okay, now, so we can say that output is not a floating node. That is correct. Okay, we have already written. Now, third point. So every time it swings to VDD or to ground, the output node swings to VDD or to ground, right? So what will happen in that case? So output node is connected to a very low input impedance node. That also makes it very less prone to noise. Now, last topic we will discuss, that is the voltage transfer characteristics. Just give me 10 to 15 minutes. 10 minutes only, not 15 minutes. So voltage transfer characteristics. So which is also known as VTC, voltage transfer characteristics, is also known as VTC. Now, if we talk about the NMOS transistor and PMOS transistor, forget about the inverter. If we talk about the NMOS transistors, or you can say PMOS transistors, we know very well the output characteristics of NMOS and PMOS, right? Any doubt? So we have already seen the output characteristics of transistors, NMOS, and let us, okay, once again we will see here. Okay, so, oh, sorry. So, okay. So, okay, here see. Hello, you can hear me? My voice is audible?
Yes, sir.
Oh, okay. So now see here. So what is happening? Okay. So here we need to connect the input signal. Okay. So here we are supplying the VDD. Also, this is source. Okay. Now this is V out. So here drain side. Okay. So now the capacitive load here, C load. Now this is NMOS, right? This is NMOS, this is PMOS. So let us say this is M2 and this is M1 here, no problem. Okay, so now if we know the IV characteristics of, let us say M1, that is M1 means NMOS, and output characteristics of that is IV characteristics of M2, right? then we can draw the voltage transfer characteristics. How we can plot, I will let you know. So let us discuss about the governing equations for the above inverter. So governing equations, let us write governing equations for CMOS inverter. Based on that, we can draw the output characteristics, that is transfer characteristics, voltage transfer characteristics inverter. Okay, so first let us discuss. We know very well, let us say IDSP is equal to minus IDSN. So IDSP represents the drain to source current for P-type MOSFET, and IDSN represents the drain to source current for the NMOS transistor. So because of the current continuity, we are getting the negative signal. So magnitude will remain same, only the direction will change. Right. Now, here see, if you see the circuit here, right? So let us see this. So what will be the voltage for this? What will be the representation here? Yes. For NMOS signal, for NMOS transistor, what is the magnitude of gate to source voltage? That is, it will be positive or negative? Yes. When the NMOS transistor will start operating, for negative gate to source voltage or positive gate to source voltage? Yes.
Positive.
Positive. Very good. So here, so this is the first governing equations. Now this is, let us say this is equation 1. Now VGSN, if you see the circuit, then you can find that it is equal to VGSN, that is gate to source voltage for NMOS, which is equal to input voltage V in. Okay, this is the second equation. Now if you see DSN, that is drain to source, if you see the drain to source, this one, okay, let us draw here DSN, right? Drain to source, DSN voltage, that is voltage, VDSN means voltage drain to source for the NMOS. Then you can easily understand that it is equal to V out. Okay, so VDSN, which is equal to V out. Okay, now we are interested in writing the equations, that is VSN, VSP, VGSP, that is gate to source voltage, for this way VGSP. So if I ask you from the circuit diagram, if I ask you to write the equations for VGSP, then what will be your answer? The VGSP, you can see here, this is equal to input voltage minus VDD. If you see the circuit diagram here, so gate to source voltage for PMOS transistor, it will be equal to V input minus VDD. And similarly, if I ask you to find drain to source voltage for this one, this one will be, let us say this is here VDSP. So which will be equal to what? V out minus VDD, right? So okay, now so VDSP, that is drain to source voltage for the PMOS, which will be equal to output voltage minus VDD. So these are the governing equations for the inverter. Now, if you see these equations, you can write that for input voltage for PMOS transistor, so which will be equal to VGSP for plus VDD. So what will be the nature for the gate to source voltage for PMOS transistors? It will be positive or negative? Because we know very well, for the NMOS transistors, gate to source voltage should be negative, it should be positive, right? So what will be the voltage, gate to source voltage for PMOS transistors? It will be negative or positive?
Negative.
Negative. Very good. Right. Okay. So if you understand, then definitely you can draw the voltage transfer characteristics. Now from here, so V out, which will be equal to drain to source voltage plus VDD. Now, so we will see the characteristics. Okay, now, how we are saying that, let us say we need to understand how we are saying that VGSN is equal to V in, because some of the students maybe they are not able to understand VGSN. We are telling that is which is equal to V in, but how? Because if you know the rule of potential difference, then you can say that VGSN, which is equal to VG minus Vs of NMOS transistors, right? So if you see the gate, a gate terminal of this NMOS transistor is connected to input terminal, right? Input voltage. However, if you see the source terminal, this is source terminal of NMOS transistor, which is connected to ground. So what would be the potential for ground? It is 0 or some voltage is there. What is your answer? The Vs for the, that is source voltage for the NMOS transistor, it is 0 because it is connected to ground, right? Connected to ground. So now you can say that VGSN, which is equal to GN, not exactly GS, so GN, so which is equal to input voltage. Right, now we have to understand, okay, how you can say that VDSN is equal to V out. We can also correlate this way, VDSN, which is equal to V out, we are saying. So how? So VDSN, which is equal to VDD, we can say, minus Vs of N. So we know very well the source terminal of the NMOS transistor is connected to ground. That's why this is VDD, or you can say V out. Now we will see the characteristics of, give me 5 minutes. Okay, so let us see here. We know very well the characteristics of IV characteristics, that is, if you see that, let us say this is VDD and IDSN. Okay, IDSN means the drain current for the drain to source current for the NMOS. So if you remember, then we were getting the currents like that, right, for different VGS, right? Let us say VGS, which is equal to 5 volt. Here let us say VGS is equal to 3 volt. Let us say here the VGS is equal to 2 volt, and here VGS is equal to 1 volt, and for VGS 0 there will be no flow of current. Remember, this was the characteristics for NMOS transistor, output characteristics of output IV characteristics of NMOS. That is true? Yes. If you say yes or no, then based on that I can correlate the IV characteristics of PMOS transistor. So just say yes or no.
Yes, sir.
Okay, now, so if you divide the coordinate system, so this is known as first coordinate, this is second, this is third, and this is fourth. Okay, so if for the NMOS transistors, you are getting the positive drain to source current, and you are applying the positive VDD and positive gate to source voltage, right? Now, we know very well for the PMOS transistors, the current will be negative, right? And the gate to source voltage will also be negative, and VDD will also be negative, right? So which coordinate we will have to follow for that? Where you get both the quantity negative, that is voltage and current, in which coordinate? Yes?
Third.
Third coordinate, yes. So the IV output characteristics of PMOS transistors will lie in third coordinate system. So you can see here now. So this one, this is the, here this is IDN, that is DSN, drain to source current for the NMOS. So here I am representing this is current I, drain to source P here, let us say. So drain to source for PMOS transistors. So it is in, you can say that as we increase the gate to source voltage, the current is increasing, right, with a negative VDSP VDD, you can say, or VDS, you can say, drain to source voltage. It is not going to, the meaning will remain same here, right? So you are getting the current in third quadrant. Okay. Now, if you shift the signal, let us say let us say VDD is equal to 2.5 volt. Okay. So as per the equations for the input voltage, as per the if you relate for the PMOS transistors, let us say V for the inverter, you can say, so V in input voltage for PMOS transistors will be equal to V GSP plus VDD, right? If you see this, let us, I'll show you how it is possible. If you see here this is expression for the input voltage, where it is input, let us say this one, input voltage for PMOS. So this is the input voltage for PMOS, right? And this is for the input voltage, input that gets to source voltage directly for input for NMOS. Okay. So here if you see the graph, see the equations here directly, you can correlate. So V in, which is equal to VGSP, right? VGSP plus VDD, right? Okay. So VGSP, let us say this is minus 2.5. Okay, minus 2.5 VGSP, and VDD we have assumed that is 2.5. So for this, if you take the mirror image of this current, then where you will get here, right? Similarly for VGSP minus 1 volt, minus 1 plus 2.5. So it will be 1.5. So for 1.5. Any doubt in understanding this term, this equation, this graph? Yes?
No, sir.
Okay. Now, why we are doing this, we will understand. Now, for the PMOS transistors, what is the V out? What is the expression for V out? The expression for V out is, if you remember, the V out is equal to V DSP, drain to source voltage, plus VDD, right? Plus VDD. So what is VDD? See, VDD is, we have already assumed that is 2.5. So drain to source voltage for the, oh, this is 2.5, right? So now if you, right, so now the signal is here, graph is here, that is in second quadrant. So from the third quadrant, we have shifted to the second quadrant. Now again we are trying to shift this signal, this current, in the first quadrant, right? So what we will have to do that? So this is the signal, right? This. So this much, if you are able to shift in this direction, then you can directly shift this one to the first quadrant, right? So how we can shift? So V out is equal to, we know very well the equations for the PMOS from the Gaussian equations. So V out is equal to VDD plus VDSP, right? So to VDD we have assumed 2.5. So 2.5 plus VDS. So in this way you can shift in the first quadrant. Now, so we know very well now, if you, this is the final, this is the final IV characteristics for the PMOS, right? And for the NMOS, we know very well this way. Sorry, wait. For the PMOS, for the NMOS, this is the characteristic will look like this, right? For different VGS, or different VGS is equal to VN in case of inverter. VGS for N transistors, right? So we have to now merge on the single device. Let us say this is V out, and this is, sorry, this is V. Okay. Now we have to merge exactly. So here we are in here. So this is the current. This is the V out voltage. So we know well this dark, because this characteristics, this is for the NMOS. So this is for the NMOS, and this lighter, this we know very well. We have shifted the signal in this way for the PMOS. So we are merging. So if you merge both the graphs, and if you try to plot the drain current for the output with respect to output voltage, then you will get the graph in this way, right? So from this curve, you can extract the voltage transfer characteristics. So let us focus here how we can extract. Let us say the Vn here the V in for the NMOS, V in is 0. So for 0, where is the point is cutting? Means we have to find for NMOS and PMOS the intersection point. First of all, we need to locate the intersection point. So let us say for example, V in is equal to 0.5. So V in is equal to 0.5. The current is this one, right? For NMOS, the current, and for NMOS, the dark. This is dark. This is for the NMOS, and lighter one is for the PMOS. Always remember here. So for V in is equal to 0.5, let us say the point is here. So for this is for the NMOS, right? For the PMOS, you have to locate the point where it is intersecting. So for 0.5, so let us say this is. So this is for the this is for the PMOS, and this is V in is equal to 0.5. So this is for the NMOS. So point is here. Similarly, for V in is equal to 1. So V in is equal to 1. If you see, so this dark line is for the NMOS, and this one, if you see the V in is equal to 1, so let us say where it is intersecting at V in is equal to 1 for the NMOS. So this point. So at this point, it is intersecting. So similarly, we have to find the point of intersection for the same input voltage for both the cases, that is NMOS and PMOS. So if you see, so the total division is like that, right? So here, if you see, so based on that, so this region, so if you see the region, we have to, this region we have to divide because we don't need. Because either we apply the low input signal or logic 0 signal or logic 1 signal in the input of the inverter. So this region is of interest, and this region is we have to divide. We have to divide this region because this is not interested. This is not interested, right? So now, so based on that, what we can observe from the previous graph, that for the input range for this one, that let us say 0 to 0 to 1.5, you are getting, for this signal, you are getting that NMOS is off. However, PMOS is on, which is in linear mode, right? So you are getting for this much input signal, you are getting logic 1 output. This is V out, and this is V input. And for this range, you are getting the logic 0 output, right? So here you can say that NMOS is off, PMOS is linear, and for this region, what will happen? NMOS will be in the linear mode, linear operation, and PMOS will be off, right? So this is the voltage transfer characteristics of the inverter. So any doubt here? Yes. If any doubt, then you can ask me here.